Hello everyone, my name is Pedram and I'm a professor in data analytics. Welcome to another episode of Deep Learning. Alright, in the past couple of videos we talked about the theory of deep neural networks, and in this one we want to see how we can implement it in Python using Tensorflow. So let's go to the GitHub folder for the course, Deep Learning USU, and then we go to Lectures, Module 4, and there's a folder here, Deep Neural Networks Python, and we're going to work with this one. So the dataset that we're going to work with is called Employee. So this is a dataset that we already saw when we were doing machine learning using PyCaret. So this is a dataset that I'm getting from the PyCaret package. Okay, so let's open it up. You can either run it locally on your local computer, but you have to have TensorFlow installed, or run it in a Google Colab. So either way works just fine. Just be aware, if you want to utilize the GPU and you don't have GPU already on your computer, local computer, so it is recommended to you do it on Google Colab. Okay, so let me go ahead and open it in Google Colab. Make sure you make a copy of your own version. And just quickly double check by the time that you're watching this, what is the version of your TensorFlow. So I'm gonna run this anyway. I'm gonna run it on my local computer. So on the Google Colab, the TensorFlow version is 2.92, and I'm gonna run this on my local computer. So let me open it here. This is the same file, and I'm running it on my computer. So on my computer, I'm using VS Code, and this is the TensorFlow kernel that I already have. So the version that I have on my local computer is 2.11.0. All right, so let's start by importing the data set. Okay, and we're going to use TensorFlow, and for visualization we will stick to our Seaborn or Matplotlib because it's a lot easier to work with. And we also use pandas as well, so let's go ahead and do that. Let's import these packages, and again, here's the CSV file that I have access to. I think that file is also available in the data folder for the course as well, but if not, you can find it. You should be able to find it here. Yep, in the folder that we just created for this class. Okay, so this one, the Python folder. Okay, all right. So here's the data set. Again, a quick overview for those of you this is the first time that you're seeing this data set. It's a classification problem. We are trying to figure out if somebody is going to leave the company or not, right? And based on some features. The features are satisfaction level, last evaluations, number of projects that they have done, average monthly hours, time spent with the company, and work accident. This is 0, 1. This is a dummy variable. Either they have accident or not. And promotion in the last year. Again, this is another dummy variable. We have department, which is a categorical variable. And we have salary, which is also another categorical variable. Okay, so we have to do something with these categorical variables first and then prepare the data. Okay, so usually it's a good idea to start by looking at the balance of the data sets, especially, basically look at your target variable if there's a classification problem, how many classes we have, because it's going to be important what's, let's say, what activation function we use and what we're going to use for the last layer, right? So how many classes we have. So here we're going to just look at the value counts of the target variable, which is left. And it seems that 70, and I divided by the length of the data set, just gives me what percentage of the samples is basically what percentage of people left the company, what percentage did not leave the company. So 0 means that they did not leave the company, 1 means that they leave the company. So 76% versus 23%, it's not bad, right? It's not balanced, but it's not highly imbalanced either. So if anything, we should have a couple of things in mind, right? The first thing is that if you want to look at the accuracy, it's okay, we can do that. We can also we can look at the performance of the model in terms of precision recall as well. But another important thing to consider is that your model better, if you're looking at the accuracy, it does a better job compared to 76%, right? Because I can come up with a common sense benchmark, right? Let's say my benchmark is I develop a model that the model says every single time nobody leave, right? So this is a prediction of the model. For everything you give me, I'm going to predict no one leaves. And if that's the case, the accuracy of that model, that naive model, is going to be 76%. So what we're going to put together as a model here for a deep neural network, it performs better than 76%, okay? Because this is our naive forecaster. Okay, so let's quickly look at the unique elements in the data set, how many unique elements we have for each variable. And this is going to help us to figure out which variable should be categorical, which variable should be, for example, numeric, right? And there are a couple of the number of projects. I'm going to leave it as numeric because it makes sense to go from project number 1 to 2 if I increase it by 1 incremental value, right? So we say, so this makes sense. I'm going to leave it like that. Average monthly hours, this is okay. You know, time spent with the company, these are years. I'm not going to touch it. Just let's leave it like that. Work accident, so this is definitely a dummy variable. Promotion last 5 years, definitely another dummy variable. We have 10 departments, and because this is a string, it is absolutely needs to be categorical. And we're going to change that from category to dummy, right? We are going to do it one-hot encoding. Salary, the same story, and finally left is our target variable. Okay, so these are the columns, and I'm going to go ahead and make a list and put all the ones that I want to change their type to categorical variables into category, right? So let's do that. So we said work accidents, promotion last 5 year, and department, and salary. So let's go ahead and do that. Then I'm going to write a for loop to change the type of these categoricals. You can do a list comprehension, but it really doesn't make a big difference. We have only 4 of them. We need to change the type, and usually this is a fast thing. We don't need to avoid the for loop here. It's also fine. So I'm going to say for the columns in the categorical, which is a list, go ahead and change the type of these columns into category. Now, if I look at the information of the data again, now this must have been changed, right? All right, so now we can look at the description of the data, right? To just make sure that for numerical variables, we don't have many outliers, right? So, or weird observations. So it seems to me that when I look at the average and look at the max and mean, so it seems to me that this data set is pretty much okay. You know, we can move on without trimming let's say the outliers, okay? Then the important thing, the next important step is to make sure that your categorical variables are dummy variables. I personally prefer to do it this way, you know, to make sure that I have a list of categorical variables, I change the type, and then when I pass this new data frame to the get dummies function from pandas, now it's triple check that the categorical variables are the ones that I want to make them dummy, right? And we're going to drop the first one. So for example, if you have 10 classes, we're going to end up with 9 dummy variables. Okay. Now, then I'm going to make a copy of this data set to just make sure that if I need to go back to the original data set, I have access to that one. So let's go ahead and make a copy of that one. This is, of course, not needed, but it's just good practice, especially if your data set is not super huge, right? And again, this is deep neural network, and we're going to use it for structured data because for unstructured data, there are better networks, you know, architectures out there. For example, if it is image, we are going to use convolutional neural networks. If it is, let's say, text, we are going to apply recurrent neural networks and things like that, right? So we have better architectures which are designed to handle unstructured data. So when it comes to using deep neural networks, I'm going to apply it only to structured data, which is a data set like this, right? Okay. So we can look at the head of the dataset one more time and just make sure that the one-hot encodings are there, getting dummy variables, right? So for example, work accident 1 is here, 0 was dropped, right? Promotion in the last year 1 is here, 0 was dropped. And we had, I think, 11 departments, so 9 of them should be here, okay? All right, so again, here's a list of the columns. And this is the important part. I want you to make sure that once you're ready to go to the next step, which is splitting the data set into train test set, before that, look at the dimension of the data frame, right? So here we have almost 15,000 observations, 1,999, and 19 feet. This is 19 variables, right? Including the target variable. So this means that I'm going to end up with 18 inputs, right? And it is important. We are going to talk about it. In the theory part of the deep neural networks, I also mentioned that your first hidden layer better be not acting as a bottleneck, right? So if I have 18 features, 18 inputs, my first layer should have at least 18 nodes or 18 neurons. Otherwise, it's going to act as a bottleneck, right? So this is important. That's why I want you to just look at the shape of the data frame before going to start constructing your neural network, right? So the next step is to simply split the data. You can do that using TensorFlow as well, but there are some built-in functions that I prefer to work with them, especially if you're dealing with a structured data set, right? And so I'm going to go ahead and import from model selection this function train test split. Again, you can do it manually using TensorFlow, and this is what we're going to do for unstructured data. For structured data, we're going to stick to built-in functions from scikit-learn. I'm going to define my x and y. X is the features, y is the target variable. So I'm going to say from this data frame, just drop left and keep everything else. And make sure that the in place is equal to false. By default, it's going to be false, but I just want to reemphasize that do not accidentally drop this left from the data frame. Okay. So these are my features. So this is maybe new thing compared to machine learning, right? Because we're working with TensorFlow, and TensorFlow works with NumPy array instead of pandas series or pandas data frame. So we have to add this dot values at the end of this data frame to make sure that it's not data frame anymore. It's NumPy array. Okay. So this is because we're going to input it to the TensorFlow, and TensorFlow works with NumPy array. So now if I look at the x, it is a NumPy array with, I can check the shape of x with 18 features and 14,999 observations. Okay, sweet. This is our features. We can do the same to the target variable. I'm going to call it y. The same story. I'm going to do dot values to make sure that this is a NumPy array now. Okay. All right. So this is a compatibility issue with TensorFlow. Okay, but it's a big important step. If you don't do that, you're going to get an error when you're trying to train the model. All right. Now, again, we're using this train test split function from scikit-learn package. I'm going to say this is my features, this is y, target variable. Let's do a test size of 20%. So it means that the train size is going to be 80% and a random state 500. If you want to see the same numbers as I do, you can set the random state to 500, but feel free to pick any random state number. Okay. So let's go ahead and run this. Now we can quickly double check the shape of our train set. Again, 80% of that 14,999 is going to be 11,999, and this is the 20% of it, right? About 3,000. Okay, so test set, train sets, and remember these are NumPy arrays, and we are ready to go to the next step, which is scaling the features. Okay, so in deep learning, scaling features is kind of a must, right? Because we want to avoid gradient vanishing or exploding for specific, let's say, features or at specific neurons, right? We can normalize the features. We can use standard scaler. You can use min-max scaler. Depending on the data frame that you're working with, either of them can work, right? Usually standard scaler works just fine for a data set like this. For example, the employee data set that we're dealing with, and this is what I'm going to do it for this exercise. But for, I don't know, for example, if you're doing image processing, we are dealing with pixels, and each pixel can take a value between 0 and 255. Usually there we do min-max scaler and we just set it between 0 and 1, right? Again, depending on the type of a data set, you can come up with different scalars, and you can try different version of scalars and see which one performs better, right? But in practice, usually this standard scalar is the one that we're going to stick to. Okay, so let's go ahead and import min-max scalar and standard scalar from scikit-learn pre-processing. Again, this is one thing you can do directly from scratch in TensorFlow, but I would rather to use these built-in functions. So we're going to work with the standard scalar. I didn't need to import the min-max. I just wanted to show you that this is also available. Okay. Then I'm going to create an object. Let's call it scalar, because this is something that's going to scale our data. Let's call it scalar, and it is as type of, this is a class standard scalar, so this object is a class, right? Now off of that object, I can do fit or fit transform. Okay, so what are we doing here? Remember, I need to transform my train set and test set, the features, right? We usually don't transform the target variable, especially if it is classification like this. I have 0, 1 for target variable. There's no point of transforming that one. You can if you want, but there's no point of doing that. And another thing you should be aware is that when we're doing the transformation, we usually, it's more than usually, right? We have to do it this way because in order to avoid data leakage or any information leakage between train set and test set, we have to make sure that we use the train set to fit our scalar, okay? So if you want to fit a scalar, because guys, remember this is standard scalar, so it means that we need to come up with an average and a variance. So take the average out of each observation divided by standard deviation. So this is standard z-score standardization, basically, right? But I'm gonna say the parameters of this transformation, it's gonna be the average in the train set and the standard deviation in the train set. So that's why off of this scalar, I'm gonna say fit transform. I could do it in 2 steps. I can say let's fit, so let me write it down. I could say something like this, x train is equal to scalar, and then fit, use x train set, and then in a separate step I could do, for example, the same thing, x train is equal to scalar, and then transform. Okay, transform x train. So I could do it either this way, so the small letter t, I could do it either this way or just do it in one line, fit transform. Okay, so we can do it in one line. Let's do fit transform. So we do fit transform x train, and then once the parameter of this transformation are driven from the train set, which is average and standard deviation, we're going to use that to transform the test set. So that's why for the test set we only have transform. We don't fit to the test set, okay? Because otherwise it's kind of cheating, right? There's information leakage between train and test set. So let's go ahead and do that. We can look at the, let's say, I don't know, first couple of observations of the train set to make sure that it is kind of standardized, right? All right. So that's the pre-processing part of the data, and it's an important step. Usually, again, for deep neural networks, when the data set is structured, it's not a big of a deal. It's not that difficult, and as you can see. But for image processing, or especially for text analysis, this pre-processing part of the data usually takes longer, right? So now let's talk about the TensorFlow itself. So far we didn't do anything from TensorFlow, but from now on, let's create the model, the neural network, our first neural network together, and see what are different ways of doing that. All right, now let's talk about this creating a neural network model part, right? In general, there are 3 ways of creating a model with Keras. Well, there's a typo here with Keras, right? And the first one is sequential class, and the second one is functional API, and the third one is subclassing. So each of them has their own advantages and disadvantages. So the sequential class is probably the easiest one. If you're a beginner in neural networks, or with Keras and TensorFlow in general, I highly encourage you to start with sequential class because it's super simple. You just call a sequential class from the TensorFlow package, and then the rest is just stacking the layers on top of each other, right? So this is easiest, but at the same time it's least flexible. If you want to change different metrics, you want to change your loss function, if you want to change the behavior of your solver, if you want to get access to the layers later on, if you want to add or remove some layers from your networks, you cannot do that. You cannot do it this way, okay? And so our next best option is functional API, and this is the method that I'm going to use for this course. And this is a method that most probably many practitioners, deep learning practitioners, are using, even for industry or even for doing some research. So it's pretty much like Lego style. You can add layers on top of each other. We're going to see an example in a minute. And it is more flexible. It's, of course, a lot more flexible compared to sequential class, but it doesn't mean that you have 100% control on what you can do inside the network, right? But you have access to different layers different input and output of a layer inside your networks. You can change those ones, you can rename the layers, you can rename the model. And I think the most important one, you have some interesting built-in visualizations that you don't have access to those ones if you're doing subclassing API, right? So that's why most probably many people are using functional API for those nice built-in visualizations or built-in functions that are available. And the last one is subclassing. This is fully customized, right? It's most advanced. If you're doing, I don't know, state-of-the-art research in PhD level research, you can definitely work with the subclassing API. Basically, it is using a class called model from Tensorflow, and we're inheriting from that class, and we're changing that class as we wish, right? So down the road, you can do whatever you want using this subclassing API. So this is a good thing. And the bad news is that sometimes if your network is very large or you're doing many customization, you may end up getting errors, and it's hard to find those, hard to usually debug those errors. But again, it's up to you. For this course, we will start with sequential class because you should see how it's done, and then we'll move on to functional API. This doesn't mean that, so for regards to 2 and 3, functional API or subclassing API, it doesn't mean that you have to pick either of them, right? You can mix and match, right? So for example, you can leverage the simplicity of functional API, but at the same time, you can have your custom metric, define it as a class, and then add it to your functional API. So, or the other way around, you can use this functional API inside your subclassing API. So again, you can think of it as a mix and match, but in my opinion, the best practical approach is going with this one. And if you need to customize it a little further, you define your own class and you add it to the layers. All right. Okay, so let's start with the sequential class approach, right? So we're going to say there are two ways of doing this one, right? So for sequential class, you can create a model as a list of layers, or you can create it as adding layers one by one, right? So, and of course, the second approach is preferred and it's more flexible. Let's talk about it. So from tensorflow.keras, we're going to import layers. So this is a class of layers that we can get access to dense layers. We can get access to, for example, different dropout layers and etc. simply by calling this layer, right? So let me remind you what was the shape of the train set. It is 18 by 18 features and almost 12,000 observations. This is important, right? Because when you're constructing your networks, your first hidden layer should have at least as much number of neurons as your features. Otherwise, you are not getting the complexity from the networks that you require, right? So the network is not able to learn the complex pattern because you're decreasing the dimension in the first layer. If the first layer has if input has 18 features and you only add, let's say, 10 neurons or units in the first layer, it is going to work as a bottleneck. And we saw that in the TensorFlow visualization in the theory part, why that's the case. Okay, so if you're curious, just check out that theory lecture, part 2 of deep neural networks. Okay, so the first approach of doing sequential class is list of layers. So what does it mean? It means that let's go ahead and create a model. I call it model underscore LL, list of layers. And I say from keras dot sequential. So this is a class. And then what do you want to put inside that sequential class, right? I'm going to say from layers, give me a dense layer, right? We call it dense because, all the nodes are connected to each other, right? Unit, this is a number of nodes that you have. So let's say we start with 18. It can be any number above 18. But let's keep it simple, say 18. And the activation function is ReLU, right? So why 18? Why ReLU? Again, there is no magic to that. You can try different units, different activation function, and see which one performs better. But as we talked about in the theory lecture, ReLU usually performs really good, no matter what kind of data set you have. ReLU is working decent if it is used in the hidden layers, right? So we're going to stick to ReLU, but you can go ahead and try different activation function. You can, for example, in the you can use 10H. You know, we don't do sigmoid in the middle because 10H is more symmetric. We talked about it in the theory lecture. And yeah, you can pretty much use, for example, leaky ReLU and see which one is going to perform better. Okay, so either way, this is our first hidden layer. Then we have to add a comma and then add another layer to that. So this is the second layer. For the second layer, we have 8 nodes. Again, why 8? I have no idea. You could try a different number, right? But the goal is to just try to figure out the pattern, the complex pattern in the data in a hierarchical order, right? So this is the next layer. So we go with a smaller number of neurons. You can go with a higher number of neurons and then come back to a lower number of neurons. Again, it's up to you, but let's keep it very simple. And I know that this is a structural data and it's a simple classification for structured data, and usually a couple of layers is going to do the job for us, right? If it is not enough, we're going to come back and add more layers. Okay. Activation function ReLU, and we're going to close the sequential class with the output layer. So on our output layer is also dense. We say number of nodes at the end of it is 1, and the activation function is sigmoid. So why? I want you to maybe pause the video and think about it. Remember, this is it's a binary class classification. So we're looking at the target variable, which is left. If somebody leave the company or not, right? It's a 0, 1. So we are going to end up with 1 unit, and the activation function is sigmoid. It's going to assign some probabilities. So if the output, for example, is 0.9, it means that 90% probability that someone is going to leave the company. Okay, we are going to call it left. If the probability is 0.1, we say, if your threshold is 50%, we say, okay, they're going to stay with the company. Okay, so this is our model LL, model using sequential and with the list of layers approach. Okay, now the model has been created. Okay, let me say, okay, I haven't imported Keras yet. So let me go ahead and import from Tensorflow, import Keras. So we need to import that one, and then let's construct it again. Okay, now the model has been created. This model is created, but is not built yet. So there's maybe this terminology we should be aware. So we created the model, but it's not built yet. So, and when the model is not built, you do not have access to the weights, or you cannot see the summary of the model. So we can go ahead and build the model. How do we build the model? We have to say this is the input layer. And now with this input layer, you can go ahead and use the function build. Okay. So, and this is exactly what we're going to do. We're going to say off of this model that we created, model LL, let's go ahead and build. And then you have to pass, this is the mandatory one, right? You have to pass the input shape, right? And the input shape, remember, it was 11,999 and 18. And we had this amount of number of observations and 18 features, right? So we're going to do it like this. We're going to say the input shape is none, and this is the second element of my X-train shape. So this is, if you do X-train shape 1, it's going to give you back number 18, right? And then we're going to use none and 18. So this is the shape of the data. Remember, why we're going to use none? Because we want to have a model that we can pass as many inputs as we want, but the number of features is important. If we number of features, we have to specifically tell what is that number. It's here, it is 18. Okay, now let's go ahead and run this. Okay, the model is built. So this means that now I can get access to the weights, and of course the weights are going to be randomly initialized, so we can look at those random initializations. And once the model is built, we can look at the optimized weights, right? Once the model has been trained, we can look at the optimized weight. But for now, let's look at the summary of this model. So this is the summary of our model LL. Okay, so this is an important step. I want you to be completely be on top of the fact that what are the number of parameters, what is the input shape and output shape for each layer, and etc. Right? So by default, the name of this model is sequential. We are going to go ahead and change it by looking at the second approach of sequential modeling, right? So by default, the name is sequential, and these are the layers. So the layer is, the first one is dense layer, and then we have, so this is basically my input layer because we built the model, right? Then the hidden layer number 1, hidden layer number 2. If I rerun this thing, if I build the model again, these numbers are going to just increase. It's going to go dense 3, dense 4, dense 5, dense 6, and etc. Right? So let's talk a little bit about this output shape for each layer. And again, this is something I want you to be quite familiar and be able to calculate the number of parameters manually, okay? So let's do that. This is our first layer, right? This is the input layer, the simplest one, and the shape is none and 18, okay? So if you remember from the theory lecture, we talked about the shape of tensors, right? So here, this is a rank 2 tensor, and we have basically none and 18 features. All right, now let's see what is this number of parameters and how can we do it manually, right? So let me actually remind you of the theory lecture that we had. So here, let me pull up this PDF. So this is our lecture note for the theory part. We're dealing with the standard neural networks, right? This is our deep neural networks. So input layer, hidden layers, and output layer. So in our case, the input layer has 18 nodes, and the hidden layer has also 18 nodes. So let me go ahead and change it to 20 because I don't want you to get confused. So let's go ahead and change this one to 20 and build the model again. Okay. And now let's calculate these numbers, right? So again, 18 inputs, 20 the nodes for the hidden layer. So how many of these weights do we see? It's a multiplication of 18 by 20, right? And then I need to make sure I add 20 bias term as well. So 20 parameters, 20 Bs for the bias term. So we're going to end up with, let's say the input was 18, multiply the first hidden layer has 20 nodes plus a 20 for the bias terms, right? So this is how we get this one. And now we're going to go from first layer to the second layer, right? So in first layer, we are going to look at that. We are going to have 20 of these. So here, we have 20 of these nodes, and in the second layer, we have 8 of these nodes, right? So how do we get this 168? It's going to be something like this. 20 multiply, we have 8 nodes here, plus how many bias term? 8 bias terms, right? So we are going to get 168. So this is our 168. And then finally, let me add that one too. For the last layer, we go from this second hidden layer to the last layer, right? So this is the easiest one. So we said that we had 8 nodes in the second layer, and we're going to add and 1 node. So we have to multiply it by 1 because there is only 1 output, plus 1 bias term for the one output node, right? So this is where we get the number 9, okay? So this is something I want you to practice, play around with different numbers here, and then go ahead and recalculate this thing. So for example, let's do it for 18. Yeah, let's do it for 18. And then rebuild the model, and then look at the numbers again, right? So 342. So what does it mean? I have 18 by 18 plus 18. So something like that, okay? So 342. And then lastly, let me go ahead and change it to 22 and keep it like that. Okay, so this is a network, or let's bring it back to 20. This is a network we're going to work with, right? So I feel okay with this network for now. So we're going to train the model and see how it performs, and if we need to make changes or add, remove layers. Okay, so just make sure before I push it to repository, we get the right numbers. Okay. So this is our 380 thing, okay? All right, so we are still talking about the sequential way, right? We're using the sequential from Keras, but we said that there are two approaches. The first one was list of layers, so this is what we did. Let's look at the another one, which is adding layers one by one on top of each other. So if you ended up doing sequential approach, I encourage you to do it this way, adding layers, because it is more flexible. You can change the names if you wish, you can comment out the layer, and etc., right? So let's go ahead and do that. So we're going to say, we're going to create a model, and the model is, we had it already reset from Keras, import sequential, and we can change the name, right? So I can say name is my classification model. So this is the name of the model. So that's your first line. And then now you have a model, you can go ahead and add, guys, remember, I call it model, so this is different than model_LL. So I want to make sure that these models are different, right? So now this model, I'm going to add a layer. Okay, so I say from layers, and remember we already imported these layers up there. Here, we already imported these layers. So from then, and say add layers, and there's this input layer. So I'm going to go ahead and add the input layer right in the model. Now it means that once the model is created, it's at the same time built as well. So it's built on the fly, right? Because we are saying that this is the input layer. So what is the shape of the input layer? So there's a slight difference here. This is the shape of the input layer, not the shape of data frame. Here, this is the shape of a data frame. Okay. So look at that. We're going to say the shape of the input layer, how many, this is 18 nodes, and we're gonna add a comma and with a space, right? So the reason we save it like this, because in the theory part we talked about it. Let me bring that one here, this one, right? We said that if you have a vector rank 1, because this is my input shape, right? We want to say, okay, 18 nodes, take it, right? And then, but we don't say shape is equal to 18. We say shape is equal to 18, comma. We're going to input it like this, right? Even though it's a rank 1 tensor, but we want to define a shape like this. So that's why you see this comma and then nothing there, okay? This is shape of each sample, by the way. So each of the samples have this shape of 18 features, and of course we save it like this. All right. Then the next layer, we're going to add another dense layer on top of the previous one, right? So I'm going to say 20 because we changed it. Activation value, and look at that, this is might be something new, right? We say, okay, the name is first layer. Then second layer, the same story, call it second layer. And finally, output layer. Let's add that output layer. And as you can see, we are building these models on top of each other, right? The layers on top of each other. One unit, activation function sigmoid, and the name output layer. So now when I press run, this model is being created and built at the same time. So this means that I do have access to the summary and the weights right now. So I can say model.summary, and these are the numbers, right? So the difference between this one and this one is in namings, and once down the road you want to comment out one layer, it's a lot easier to do it this way, right? So here, you see, when I run this multiple times, now it dense 15, dense 16, dense 17. You might not like this, right? So you want to come up with your own names. You say, okay, this is my model called my classification model. First layer, second layer, output layer, and these are the parameters, right? And you already calculated these numbers. So just to be consistent with the previous one we were doing, we have 18 features. I need to multiply it by 20 and then add 20 bias terms. And 380. Then in the second one we have 20 inputs for the second layer, and then 8 outputs. We need to add 8 bias terms, 168, and etc. The last one is 9, right? Now that the model has been built on the fly, we can get access to the weights, right? So the model has not been trained yet, right? This is just the random initialization for the weights, right? So these are the weights, and in general, how many parameters we have. So first layer has 380, second layer has 168, third layer, the output layer, has 9. And this means that if you add these together, you get to the number 557. And you will see something here. It's called total parameters 557, trainable parameters 557, non-trainable parameters. So what is this? So usually we deal with the trainable parameter. The trainable parameters are the parameters that are being updated in the back propagation process, right? Sometimes you want to build up networks that when you're doing feed forward, you just want to keep track of things, right? You want to say, okay, this is iteration number what, right? Something like that. You want to keep track of things, and you're going to add those variables to the networks, and you're going to assign a parameter to keep those things, right? So those parameters are not going to be updated during the back propagation step. So if you have something like that for some of the models, this is called non-trainable parameters. So this is one way that you will see non-trainable parameters. Another way is when we are doing transfer learning, right? So transfer learning is the concept of, let's not build a model from scratch. No, let's leverage a pre-built model which has been trained on millions of records of data, let's say on a text or image data set. and then you want to use their structure and use their parameters, their weights, and then add your own, let's say, final output layer or a layer here and there, and then train only your last layer, right? So you want to say, and usually those are large models, right? A model with millions of parameters. So you're going to see, let's say, I don't know, 60, 70 million parameters that are not trainable. You literally freeze them. And then you have, I don't know, the couple of hundred or couple of thousand parameters for your own model, either the first layer or last layer or the output layer. And then you're going to make sure that your model is going to update those weights when it's doing backpropagation. Hopefully it makes sense. If not, don't worry about it now. We're going to get to that part of the course. But just be aware, in this deep neural network, everything is trainable because everything, all the weights that we have here are going to be trainable in the backpropagation step. So it means that these weights are going to get updated at each iteration, okay? All right, so those are the weights. Now, that was the first approach, sequential class approach. The second one is functional API. Let's look into the details of this one. All right, so the functional API. As we saw in the sequential model, it was super easy to use, but its applicability is extremely limited. What does that mean? It means that with sequential approach, you can have only one input and one output. And this is in practice basically very not common, right? Because usually we are going to deal with models with multiple input types and multiple outputs, right? So for example, your input can be a combination of a structured and unstructured data, an image with its data, metadata, an email with its, let's say with a subject and with the body, right? And the time of sending that email and etc. And the output can also be the multiple, we can have multiple outputs, right? You want to say, okay, at the same time, you want to have classification, what is the probability that each output belongs to each class. But at the same time, you want to have multiple of those outputs, right? Multiple of those classifications. So for that matter, we are not going to work with sequential models, right? Especially if you have multiple inputs or multiple outputs. And then we have to do functional API, right? This exercise, though, the one that we're covering, has one single input. The input is what we saw, and one single output. The output is going to be just probability if someone is leaving the company or not, right? So the steps are pretty much straightforward, actually. This is what we call, this is just like Lego, right? We are adding models on top of the previous one, so this is pretty straightforward. Let's go ahead and do that. The first layer is what we call it inputs. And again, from Keras inputs, the shape. So we have seen this before. This is the exact same thing we did before. And then we're going to say the name is my input. So this is your input layer. Now, the difference is here maybe. So remember, the name of the first layer, you call it inputs. Whatever you call this one, you have to add it to the end of the second layer, right? In parentheses, right? So this means that this is your second layer. I can call it features. So this is traditionally we call it features. You can call it anything. You can call it your X1, X2, X3, whatever, or feature layer 1, whatever you want to call it, right? So we call it features, and then it's a dense layer. I think we change it to 20. Activation value, name your first layer, whatever it was. And now I have to add the previous layer to the end of this, right? So this is where the idea of this Lego is coming from, right? So this was input, right? Now I'm going to make another layer, and this is dense with 8 nodes, activation value and name second layer. And this is going to be a continuation to the layer that I call feature. Again, you can have different names for this. And then finally we have outputs, right? So output layer is 1 unit, activation sigmoid, and basically we're adding it to the feature. Remember, this is output is coming after the feature. This feature is coming after this feature, okay? And we can go ahead and create and build the model, okay? Then you can look at the model. I call it model functional to just make sure that this is different from the model LL or model. So this is model functional. We are going to see exact same thing, but now there's a new layer, which is called your input layer. And that input layer has the shape of none and 18. Remember, we had 18 features. Okay, then, so first hidden layer, second hidden layer, and etc. The number of parameters is pretty much the same, okay? If you do things this way, model functional, the functional API, we have, as I said, we have access to some nice visualizations, and we can change we have access to inputs and outputs of each layer. So I'm going to show you an example that we're going to add another layer, let's say, at the end of it, right? But for now, let's look at this visualization. From Keras util, we can do plot model, and we have to pass the name of the model that we have. And this is the name of the output, so we can call it ticket classifier.png, right? And we can say, okay, show me the type of each layer, the type of the data, sorry, and then show me the activation function that was used in the layer, show me the name of the layers, and show me the shape of these layers, right? So we can go ahead and run this. If you run this on your local computer, you are probably are going to get an error that it needs a couple of extra packages to be installed. One is GraphViz, the other one, I think, I'm not quite sure, but there's another light package that you should install, right? If you do it on Google Colab, if you got those messages, you have to go ahead and install it manually. If you're able to install GraphViz and the other one successfully, okay, go ahead and do it. If not, don't sweat over it. It's no big deal. No, we don't need it for the course. I just wanted to show you that this is also possible. Usually, I would rather to write these things on a piece of paper when I'm putting together the network, right? So usually, I encourage you to do it on a piece of paper as well. And then once you decided what a structure of the neural network you want to have, then you're going to write it down simply like this. Okay, but this is also available. So as you can see, we have the input layer, first hidden layer, second hidden layer, the output layer, and you can see what is going inside and outside of each layer. So the first one, of course, is just one input layer. So inside the input and output is not different. But the second one, input is this, is outputting 20 because we said use 20 nodes. The second one, inputting 20 because it's coming from the pass layer, and outputting 8 because we said that node is 8. And the third one, which is the output layer, it's getting 8 nodes into it and then spitting out one output. Okay, so again, this was one good thing about the functional API. Another thing is, which I think is more important, is you can access to the input and output of each different layers, right? So remember, here we had 1, 2, 3, 4 layers. I can have access to, let's say, for example, the input of the second layer, the output of the first layer, right? And I can say, let's go ahead and add another layer here, maybe, after the output of the second layer, right? So this is very cool because it enables you to just customize the networks as you wish. You don't need to go ahead and build the model from scratch, right? So for that, we really like this property. So that's why we're going to work with functional API for the course. Okay. So let me show you the layers. You have access to the layers for sure. So if you do model functional layers, and as you can see, there's this input layer, dense layer number 1, dense layer number 2, and the output layer. Okay. So now I can say, let's go ahead. So again, the goal is to add another output layer to the second layer, right? So we want to do something like this. I want to add another output layer here. Okay. Remember, this was a model that this functional API enables us to have multiple outputs, right? Let's say I have another output and I'm going to add it to the model. So I will say features. Again, you can call it anything, right? Features model functional dot layer index 2. So where is this? Remember, index 0, index 1, index 2. So this is index 2. This is layer number 2. Where do I want to add the new layer? Do I want to add it to the input or output? So this is output, right? So usually we add it to the output, right? So this is where we are. When I do something like this, I say, okay, hey, new structure or new network, go ahead and make something right after this. Okay, so this is what I'm doing. So I call it features, and now I'm gonna make a new output layer. So again, this is simply an output layer, layers.dense. Let's say this output layer has 3 nodes. Activation function cannot be sigmoid anymore, right? Because we have 3 classes here. So we're going to use softmax. Make sure you watch the theory part if this doesn't make sense, but hopefully you know what we're talking about. and then I can call it new output layer, and this is built on top of the features that we just created here, right? All right, and then I can go ahead and look into my new model. I say the new model functional is a keras model, and inputs is inputs. We didn't touch it. You know, the inputs is already defined up there. And outputs now are two things. I have a list of outputs, right? One is outputs from the previous model. The other one is new output from this model. I don't want to call it model, from this customization, right? Okay, now I can run this. Now let's look at the summary. It's going to be interesting, right? So this is our new model functional summary. So look at that. My input, no change. The first layer, second layer, no change. This is output layer, and this is a new output layer, right? Again, the ordering comes in a way that you can put it in the list, right? The ordering matters actually. And so the number of parameters, nothing new here. Maybe this last one, you have to say, okay, let me actually talk about the connected, and I get to the number of parameters. So as you can see, the first layer is connected to the input layer. The second layer is connected to the first layer. The output layer first is connected to the second layer. Look at this one. New output layer is connected to the exact same thing, right? So we have, let's say we have something like this, and I'm attaching two type of output layers to this final hidden layer. So this is what we're doing here, okay? So now you should be able to understand how we can calculate the number of parameters in this newly added output layer. So let me actually add it here. So it is coming from, let's say where is this coming from? It's coming from the second layer output, right? So what is the second layer output? It has, this is our second layer output. It has 8 nodes, right? So if anything, I have 8 nodes, which is coming to the last new output layer. So 8 multiply, how many the nodes we have here? 3. How many the bias terms should I add? 3, right? Because this is how many bias terms we need. Okay, so if you do the math, you'll get 27. So this is where the number 27 is coming from. Okay, again, this is something that I want you to practice. You know, play around with different number of nodes and see if you can back out these number of parameters. And this is a property that we really like, you know, with, this is something that we like, so that's why we're going to work with the functional API version. Okay, so for the rest of this notebook, I'm going to stick to our model. This is the model that we created, that we put together using Sequential API, and we use not the list of layers, we add the models on top of each other. So that's why I keep the name, the simplest one model, and we're going to work with this, right? So these are the number of parameters. We talked about all these things. Okay, now let's go to the next step, which is model compile. All right, for the model compile, there are something you need to pass to the model compile, which is basically what optimizer you're going to use, what loss function you want to use, and what metrics, right? So here, if you click on the links, it will navigate you to the Keras API documentation. I can quickly show you all of them. And this one. Okay, so these are different optimizers that we have access to, right? You know, we have stochastic gradient descent, RMS prop, Adam, and etc. And these are, let me see. These are available loss functions, right? So for example, what are we doing? We are doing binary class classification. So we will use binary cross entropy, right? And yeah, these are the loss functions, and of course these are the metrics, right? So depending on if you're doing classification or regression, you can pick different metrics. So for example, mean squared error is a metric that we use for regression. One thing that is worth mentioning is that when it comes to regression, right? When it comes to regression, you see we have this loss function, which is mean squared error, okay? And because the loss function is mean squared error, you do not need to define a new metric, because mean squared error is also a decent metric that we can work for regression, right? You can go ahead and try different metrics, but because the loss function is already mean squared error in our regression problem, we can say, you know what, I'm not going to pass any metrics. But just be aware, that was just a coincidence that the loss function was exactly the same as the metric. For classification, that's not the case. For classification, we're not going to use accuracy or precision or F1 as a loss function, because basically simply we cannot, right? The loss function has better have some properties like continuity, differentiability, to make sure that the gradient descent is able to get to the global optimal, right? So for that reason, for classification, the loss functions are different. So again, for binary, we're doing binary cross entropy. For categorical, if the output is one hot encoded, we do categorical cross entropy. If the output is integers and we have multi-class classification, we do sparse categorical cross entropy, right? You can go ahead and read the documentation of each of them, and based on depending on what type of problem you have, you can pick the right one. But just be aware, for regression, it happens that the loss function is the same as the metric, right? So, and of course, for classification, the metrics can be different. So we have different classification metrics. All right, now let's go back to the notebook. Okay, so here is the most commonly used, let's say, the setup for compile for regression and classifications. And we can do, for example, if you have a multi-class classification problem, if it is one hot encoded, we can do optimizer RMS prop. Loss function, as I said, categorical cross entropy. The metric can be, for example, accuracy. The reason that I want to show you that there are two different ways that you can put the metric here, right? So you can say the first way is just directly calling the class itself, TensorFlow.keras.metrics.accuracy, open close parenthesis. So this is one way. Another way is just call the name of it, right? The name of this metric, so is just accuracy. Let me actually show you what do I mean. So if I go to metrics, go to accuracy class, again, this is what I was talking, you can say tf.keras.metrics.accuracy, open close parenthesis, or you can use the name of it, right? For accuracy, because there's not much you can do inside, we usually use the name, just say accuracy. But if you're using a metric that you can pick different values for different parameters, you want to use this version, say tf.keras.metrics. The name of that metric, and then you want to customize it inside, right? So these are basically different ways we can call these metrics here in the notebook, right? And again, if you have multi-class classification, the output is integer, like MNIST dataset. We are classifying handwritten digits from 1 to 9 or from 0 to 9. So we have 10 classes. So that's why we are going to use a sparse categorical cross entropy. Okay. And again, metric can be accuracy. For binary classification, we do RMS prop. We can do RMS prop or Atom. These are the better optimizers, both of them. And the loss is binary cross entropy, and metric can be accuracy. And again, for regression, as I said, the loss and metric are the same, right? The loss is MSE. The metrics can be also mean squared error. It can be anything else. It can be mean absolute percentage error or mean absolute error. You can have your own one, but usually if you do MSE, we don't need to assign this last one. We simply ignore it. We don't need to assign anything to that one. Okay. All right. So our problem, reminding you, is if someone is going to leave the company or not. So it's going to be binary class classification. So that means that I'm going to use, we are compiling the model, remember. This is not the training part. We're just compiling it yet. And the next step, we're going to train it. So I'm going to say, let's go ahead and compile the optimizer RMS prop. The loss function is binary cross entropy. The metric, you have to pass it as a list. Otherwise, it's going to complain. And it can be list of multiple things, right? It can be accuracy and multiple other things, and you can just list it down the road. Okay, so let's go ahead and compile a model. Now the model has been compiled. Okay, so the next thing I want to talk about is that let's do this. Let's do all these 3 steps: create, build, compile in one function. Okay, and I'm going to call that one function build model. There's a reason we do that, because when you're training the model, every single time you train a model, the weights are going to get updated. Imagine you're not happy with the loss that you're seeing of the train model, and you want to make some changes. You want to go back and change the number of nodes, you want to add layer, remove layer, you want to change the activation function, whatever you want to do. If you do that without rebuilding the model, then the weights are going to get updated on the previous weights, right? This is a common mistake. You don't want to update the weights on the already trained model. So in order to avoid that, we have to put all these 3 steps in one. Again, creating a model, building a model, and compiling it, and then put it in one function. From now on, I can simply call this one function. By calling this one function, all the weights are going to be reset to initial values, right? So this is an important step. So that's why we do it. And it's convenient. So we're going to define our own function. Usually we call it build model because basically you're building the model. And then we're going to copy and paste whatever we have there, the network that we created here. So again, it's a simple model from Keras. If you're sticking with the sequential one, but you can use a functional API here as well, right? And yeah, we use the second approach, right? We are adding layers on top of each other. So we have seen this before. So let me go ahead and change this one to 20. Just make sure that we are consistent with the previous thing we had. And then we are adding this compile part. And the return of this function is going to be the model that we created and built. And we added the compile. Let's go ahead and run this. Now I have a function. So this means that from now on, if I want to make a new model, you can call it anything. You can call it my new model, model number 1, model number 2, whatever, right? If I want to create a new model, I say this model is this build model, right? And again, once you run this line, it's going to go ahead and reset all the weights to initial values. So this is going to be important because, as I said, when you train the model, you don't want to train the weights on the previous ones, right? And if you want to make some changes to the, let's say, structure of the model. All right, we can look at the model summary. Again, nothing new here. This is the same model that we've been stick to from the beginning. All right, the next step is to, let's go ahead and fit the model. So this is a training part. So this is the exciting part, right? So now you have a model. We're going to use the fit function to literally train the model. So maybe this is one of the parts that if you want to train a model differently, or if you want to make it the training process super customizable, even the functional API is not going to do the job. So you can do subclassing API or subclassing approach. But for our course, the functional API is just more than enough. You're going to stick to that. Okay, so let's do model.fit. And so this is the core of your training process, right? The back propagation is going to be done here. So we're going to say, let's go ahead and pass the train set, X train, pass the Y set. We are going to pass the validation data as well. So it's expecting you to pass a tuple. So we are passing the test set and Y test. So we're going to, this is the name that we use for that, validation data, right? And then the number of epochs and batch size. So there are a bunch of other things in the fit that you can look at the documentation, but for now, these are the ones that we're going to work with, right? So we have 400 epochs, and let's say the batch size is 128. So we had a detailed discussion of what is epoch, what is batch size, why, for example, the batch size is in the scale of 2 to the power or something because of parallel processing. If you're already familiar, just move on. If not, make sure you watch the theory part of module 4. But what I have now here, look at that. I have, let's say, 400 epochs. And it means that it's going to go ahead and do the fit 400 times. And each epoch, it means that use the entire sample, right? And I'm going to do it in the batch size of 128. So let's go ahead and run this. Okay, so this is running the first epoch, and then you can look at it as it's being trained. Because this is a structured data, it's going to be super fast, and the data set was not big, it was only 14,000, I think, in the train set, and each one is taking 1 millisecond, right, each iteration. So as you can see, at each iteration, you see the loss and your metric, right? So in our example, they happen to be different, right? So for regression, they are both MSE, but here the loss is binary cross entropy, the metric is accuracy. So this is in the train set, and this is in the validation set. We don't care about the train set that much because we know that neural networks, because of this approximation theorem, the theory of approximation, we know that neural networks can approximate any function, as long as it's convex. And so we're not worried about the performance of the model in the train part, in the train set. It's gonna do excellent job there. So what we look into is the performance of the model in the validation set. So in first iteration, when the weights were quite random and no update, maybe this is after first update, we get, what do we get? We get the loss of 0.49 and accuracy of 75. This accuracy in the validation set should increase, right? And if you scroll down, it should increase. And at some point, it must start, maybe this is accuracy might start decrease again, right? If you look at the loss function should decrease, right? Ideally, in ideal world, even in the validation set, the loss function should strictly decrease, but that's not the case because we know that the network is gonna let's say overfit, and at some point this is gonna come up again, right? So this is, now the model has been trained, right? So the model has been trained, and I can go ahead and look at some evaluation metrics. So this is the part that I was referring to, guys. Now, for example, you look at these performance and model evaluations and performance, look at the loss versus the epoch plot, and you're not happy with that. For example, you're not happy. You cannot go back here and change the, let's say, batch size to another one, or change the epoch, or change something, right? Because if you do that, the weights are going to be updated on top of what you already have. So this means that you have to go back and construct the model again from scratch. So that means that you have to run this line, right? Because you have this built model as a function already, you don't need to do that. You just call model is equal built model again. So it's going to reset the weights and refit the model for you. Hopefully that makes sense. All right, now for model evaluation, and we can, let me actually show you what does this model contain now. This model, if I do model history and then history, it's going to give me a dictionary, right? So it's a dictionary that the first key is going to be loss, and the second one is going to be, so I cannot see it here, but it's going to be the metric, performance metric, right? So I'm going to put it in a nice data frame, no pandas data frame. So let's do that. So I call it loss data frame. From pandas package data frame. So let's, because this is already a dictionary, so I don't need to do anything else. So I just do model.history, and then we can look at the tail of the data. The tail, because I want to see what is for the last iteration, how the model is performing, right? So in this 400 epochs, it seems that our model get into a point that the loss is 0.07 in the train set and 0.12 in the test set, okay? And probably somewhere in between we have been doing better, or maybe we didn't need to train the model for 400 epoch. We needed to stop somewhere, right? So this is the point that we are going to add this regularization to the model, right? But before that, let's plot this. We're going to say from this data frame that we put together, show me the loss and value loss, and simply use the plot function. Okay, so this is how it's going to look like with our structure that we have for a neural network, right? So as you can see, the model is kind of overfitting at some point, right? It's not decreasing anymore, and it's just, we cannot visually see it, but at some point it's increasing, right? So we can do regularization now. We can do either early stopping or dropout regularization, or a combination of the two. So we are gonna consider all these things, okay? Okay, so let's start with regularization. So we talked about it in the lecture theory, different methods of regularization. There was a part 2 of our deep neural networks lecture, right? We said that we can do L1, L2, dropout, early stopping, data augmentation. For structured data, and we talked about the details, dropout and early stopping are our choice, our better choice. So let's go ahead and do that. So I'm going to start with the early stopping. Okay, so early stopping is a callback. So what do we call callbacks? Callbacks is something in TensorFlow that you can literally call back to a specific part of the training process, right? So there are multiple callbacks available in TensorFlow package, but the ones that we are mostly using is called model checkpoint and early stopping. So I can go ahead and import both of them, and I will show you how to use either of them. But usually this is used for, again, regularization. This is used for, so for example, you want to say, once you're training the model, keep the best performers and then make a checkpoint, right? for whatever reason, if it gets disrupted or if the training is taking so long, for this data is easy peasy, right? It's a structured data with few observations. So we are not going to use the model checkpoint here, but hopefully you get the idea that if the training part is taking so long and you want to make sure that you don't lose some of the information, so you're going to add checkpoints in between, right? Okay, so let's go ahead and create an object for this early stopping and model checkpoint. So early stopping is a class from the, did we import it already? Yeah, we already imported, sorry. So we're gonna, from tensorflow.keras.callbacks, we're gonna import them separately, early stopping and model checkpoint. And for early stopping, what we need are, these are the important parameters that we need to pass. First of all, what do you want to monitor, right? When should I stop? So I say, okay, monitor the validation loss, not the train loss, right? Just monitor the validation loss. And what is the mode of this loss function that you're talking about? Here is min, because remember, this is binary cross entropy and we're minimizing that. Usually for the loss function, we're minimizing, and you can leave it as empty. Automatically, it's going to pick if it is a min or max. And it's smart enough to figure it out, but for me, just double check that this is not, it's not going to get me a hiccup down the road. I say, okay, let's go ahead and set it manually to min, right? Verbose is basically telling you how much information you want to see in the output, right? I can say verbose is equal to 1. It's going to give me maybe one line of explanation what's going on, right? I can do verbose is equal to 2. It's going to give me more information, and etc. Patience is after, so it tells you that after how many epochs you want to stop early. So this is basically to avoid noise, right? Because let me go back here. You see, this is a little noisy, right? It goes up and down, up and down, up and down, right? Because remember, we are doing mini batch gradient distance. The batch size was 128, so the path is not smooth. It has some ups and downs, right? It becomes noisy. And we want to make sure that if I say, for example, patience is equal to 1, it's just looking for the epoch that's it improved once and it's going to stop there. I don't want to do that. I want to make sure that this happens at least 10 times, you know. So I'm waiting for 10 iterations to the validation loss gets degraded and then stop there, right? So you can change that one. There's no magic number to this as well. You can do 20 to 30 to be more conservative, or I don't know, you can just cut it right there. You can say single digits, 2, 3, right? And model checkpoint, again, from this class, what we need to pass is the same thing, monitor, you know, validation loss. And we can say save best only, true. So again, we're going to see we are going to add this model checkpoint, but if I say save best only, it's going to save the best performing model only, obviously. And of course, you have to give it a path, right? I say this is my model checkpoint.keras. So let me actually pull up the folder. So this is the folder that we are working on, right? So right now, there's only this ticket classifier that we created up there. I think this is what we created. And then there's nothing else, right? We're going to add some checkpoints here, and we're going to save the models later on. So we're going to add some stuff here. Okay, so let me keep it there. All right, so that's the path. And if I just go ahead and add it to the model, it's going to create this model.checkpoint.keras, underscore checkpoint.keras. Okay, so I'm going to put these two checklists in an object called checklist, right? And as the name suggests, it's called callback list. And it's expecting you to pass your object as a list. So I'm saying, okay, this is a list of 2 checkpoints, callbacks. The first one is early stopping. The second one is model checkpoint. Okay. Now I have the list of my callbacks. Where can I add it to the model? Let's look into that. Okay. You see, I'm going to go ahead and reset the entire thing by running this one line of code. Hopefully it makes sense now why we need to do it this way, right? Why we need to define our build model, take that one extra step, because later on we're going to rebuild this model from scratch. And I'll do that because when I want to train a new model, I don't want to train them on the previous one, right? So this is an important step that usually students forget. Okay. All right. So now this is in the training part that we're going to add the callbacks. We say model.fit, the same stuff, X train, Y train, validation set, number of epochs. We're not going to touch anything here, batch size. And now the only thing we add is callbacks, and it's waiting for a list. So I will pass my callback list. Okay, this is my callback list. Okay, so this is the second time that we are training this model. Now with the difference that we added this early stopping and we added the model checkpoint. So as you can see here, while the model is being trained, it starts creating checkpoints right away, right? So as soon as it finds the best model, it's gonna save it. So this is my model underscore checkpoint.cures. So it means that if for whatever reason this get interrupted, or I don't know, you're working on Google Colab, you get disconnected, you have at least some point to refer. So inside this checkpoint, there's basically the structure of your network and the weights, the parameters. All right, so we can scroll down. Right after, so it seems that after 81 epochs, we get to the algorithm is stopped. And remember, our patience was 10, so it means that it has been 10 epochs that the validation loss was degraded. So let's stop there, and the number is 81. Now we can look at the new plot of loss function versus number of epochs. So this is a good one, right? So this is what you want to see. So if I see the plot like this for the loss function, it's okay. It means that, look at that, both the train set and validation sets are learning something, are learning the pattern in the data. And at some point your model, of course the validation is not outperforming the train set. This is quite normal, right? And so I'm okay with this model, right? I'll take it. I'll say that, let's say this 81 is a good number of epoch. Let's train the model up to then, and it guarantees that the model is not overfitting. We don't get something like this. So the model is overfitting. We don't want to get that. So let's say this is my winning model, right? So let's keep that in mind for now. And I'm gonna do the dropout and see which one is better, right? So let's add another regularization, which is dropout. And usually we add the so let's see how it's done. So I'm gonna say, let's define a model. We call it build model with dropout, right? You can call it anything. This is pretty much the same as the previous one, but now we're adding some dropout layers wherever you want, right? So I say, this is my input layer. This is my first hidden layer that we change it to 20. Again, same activations, we can stick with the names. And now I'm adding some dropouts, right? So the dropout is, let's say 50%. This is a number that works in practice, and it's gonna drop randomly. It's gonna shut off 50% of the neurons randomly. However, for this exercise, this is not gonna work, right? Even before running the model, we're suspicious that it's not gonna work because of multiple reasons. First of all, this is a relatively small neural networks with, let's say, 20 layers at the first one, 20 neurons at the first layer, and 8 neurons at the second one. And there's a good chance that the validation set performance is going to be better than the train set performance. So let me do the visualization, and I'll talk about it why. We already talked about this in a lecture video, but I'm going to briefly mention it here because this is important. So I added dense layer right after the first hidden layer, and then I added the dropout layer right after the first hidden layer, and we're going to add another dropout layer after the second hidden layer. The rest is pretty much the same, same optimizer, same loss function, same metric. Okay, let's go ahead and run this. Now I have a function called build model with dropout. So I'm going to say, let's go ahead and make an object called model with dropout and assign that function to that. So let's look at the summary. This is pretty much the same as before. Now we have extra dropout layers. So this is dropout layer number 1, dropout layer number 2. I could have changed the names as well. Okay, so now let's fit this new model. So I'm going to say model with dropout. Let's fit exact same thing, right? Let's create a checkpoint. Let's create this early stopping and etc. Right? Let's run this. Okay, so now let's see, where does it stop? So we are going through 70. We were stopped previously by 81. Now it's going beyond that. So it stopped at iteration epoch number 100, right? So let's look at this plot. So this is what I was talking about, what I was referring, and I was suspicious a little bit, right? So let's see what's going on, because it is important to understand. First of all, what we are what we don't like at all is that the validation loss is better compared to the train loss. So, and you might wonder why, what's going on. And look at that, even in a train loss, it's not, the path is not smooth, simply because we are randomly dropping out 10 features from the first layer, or 10 neurons from the first layer, and 4 neurons from the second layer, right? The reason that you see that the validation loss is outperforming compared to the train loss, which doesn't make sense, right? The reason is that the dropout layer is only applied to the train data. Okay, so when you're adding the dropout, it's applied to the train data. It means that the blue curve is plotted based on the dropout network. The orange curve is plotted based on the not dropout network. So this is a sign that the dropout is somehow overkilling it, right? Not overkilling it. The idea is that it's making the model simpler unnecessarily, right? So that's why in the train set, the network is not learning much. And in the test set, when we're adding back those number of neurons, this is going to perform a lot better. And remember, guys, what is, in my opinion, what is killing the performance in the train set here is basically this bottleneck that we have. So remember, the input shape was 18, right? And in our first layer, we had 20 neurons. If I kill 50% of these 20 neurons, so I end up with 10 neurons, then the input layer is 10. The input layer is 18. The first one is 10. So this is going to act as a bottleneck. So that's why we don't get the complexity of the pattern in the data, because you go from 18 features to 10, and then you go to 4 and then an output. So that's probably oversimplifying the structure of the model, and that's probably why in your train set it's not doing well. And if you're wondering why validation set is okay, because again, the number of neurons are back to normal. 20 first hidden layer, 8 second hidden layer. So this is important. I want you to keep in mind that this is what's happening if you see something like this. Okay, so because of this, I'm not happy with the model with dropout. So we're going to stick to our model without dropout, right? So the model without dropout, remember we call it model. It was just model. So let's look at the performance of that model in the test set. And depending on what you pass when you're compiling the model, we just say there's a loss in accuracy. So the loss is 1241 and the accuracy is 96.17. So this is great. This is doing an excellent job in the test set, right? We can look at the numbers for model with dropout. The numbers are 96.30% accuracy, and the loss is 1287. So the loss is a little worse than that. But again, so here it turns out that both of them are doing decent in the validation set. But if you're wondering again why that was the case, hopefully you have the answer now. Okay. So lastly, let's talk about model predictions, right? Let's say we want to make some predictions with the model with dropout. Again, it really doesn't matter. You can just replace it with the model. And I'm going to create an object called, these are the predictions in the test set. And these are probabilities. So by default, if you do predict and pass a test set, it's going to give you back the probabilities, right? So I can say y test probabilities is this. And now I can look at them if I want. So these are the numbers, right? So for example, for the first observation, for the first person that's working in this company, these are the probabilities. 6% probability of leaving, 0%, well, for this guy, 11.77% probability of leaving, right? And we need to reshape this thing. We need to reshape this thing because when you're creating this pandas data frame, so we have to say, okay, let's reshape it to -1 and everything. Basically, give it to me as a nice NumPy array, right? Okay, so I'm gonna make a data frame. Usually, again, guys, I think I said it at the beginning of this video that for structured data, I prefer to work with pandas, Seaborn, Matplotlib for visualization, and then add Tensorflow for training the model. For unstructured data, because usually there's not much to visualize like this, so we're going to stick and building things from scratch in Tensorflow, right? Even scaling the features and everything. But here for structured data, I feel okay, using and leveraging some functions from built-in functions in different packages like scikit-learn. Okay, so here is my prediction table. What I have in prediction table is y test. This is actual y's, somebody left or not. These are what the model predict. And this is what I put together based on my own threshold, right? I say, for example, my threshold is 50%. I'm going to create a variable, call it, these are my y-test predictions. I say, if the probabilities are greater than 50%, call it 1, they defaulted. Oh, not default, they left the company. If it is less than 5, they didn't leave the company, okay? So then I have two columns, y-test predictions. I can report any metrics that I wish, right? So let's go ahead and do that. So I'm going to say from scikit-learn metrics, import classification report, and imagine you're interested to false positive, false negatives as well. You can look at the confusion matrix, right? So let's do that. And I'm going to say this is classification report. The actual y's, these are from my predictions data frame, these are the y-test. And the predictions are y-test predictions, right? Hopefully you're following. All right. Then I can look at the numbers. So this is, for example, the accuracy, the overall accuracy of the model is 96%, which is a lot better than 76%. Do you remember where this 76 is coming from? At the very beginning of this notebook, I showed you that 76% of the people are not leaving the company. So if your neural network is doing anything, it should be performed better than 76%. Basically your naive model or your benchmark, right? So it's doing 96, it's okay. And even the precision recall for both classes, they're decent numbers. F1 score is good for both classes. And overall, we're happy. We're happy with what we're seeing in the test set, okay? So again, we can report the confusion matrix as well. We can look into the false positive, false negative. So these are good numbers, true positive, true negative, and these are the bad numbers, 26, 85. And these are the number of misclassifications, right? And of course, the accuracy is constructed based on that. These two numbers, add these two numbers and divide it by the total number of observations in the test set. All right, so we're almost there. The last step is to save and load the model. All right, the last one. Let's save the model. So we can save the entire model in two different file formats. One of them is save model. Usually, basically, if I do save and then if I don't pass the extension, automatically it's going to use the save model. And the other one is just HDF5, right? So if you have a model, if you have a simple model like this, like this simple deep neural network, and we can absolutely use HDF5. This is the extension is H5, and maybe it's going to be size-wise, it's going to be smaller compared to the other one, compared to the save model format, and it's a single file. And basically, for models like this, I would rather to save it as H5, right? But if you want to, for example, if you want to save your custom objects down the road that you created in the neural network, and you want to have access to those custom objects, you have to save it as save model, not HDF5, right? So that's probably the main difference. You can follow this link, and in TensorFlow documentation it talks about the differences in more detail, right? So I'm gonna go ahead and say from TensorFlow.keras.models import load model. So I'm gonna need this function to load the saved model, but first I need to save model. So this is the model that I'm okay with that. Let's say model, and this is the one that we created with Dropout. Let's save both of them. I'm going to save model, my DNN classification. This is without Dropout. This is my DNN with Dropout classification, right? So let me actually show you the folder one more time. So far we don't have these ones here, right? So we can say, let's go ahead and run this line. If I run this, it's going to create two H5 format files, right? So let's look at that. Okay, so these are the saved models, right? The first one is my DNN classification. The second one is my DNN with Dropout classification. Now that I have them saved in a directory, I can load them, right? I can go ahead and say, I can call them anything. I can call it loaded model or loaded model without Dropout or with Dropout, right? So let's go ahead and do that. Now the model has been loaded. What does it mean? It means that your trained model is loaded now. So all the updated weights, all the parameters are optimized, right? So now I can go ahead and use this right away. I can look at the summary. I can make predictions right away, right? I can say load. What is the summary of the loaded model? So this is the one without dropout. This is the one with dropout, right? So this means that I can say, for example, use either of them. I can use the load model, right? So I can say loaded model. This is the one without dropout, right? And then I can make predictions now. Predict, and then pass whatever you want. You can pass a single observation. You can pass the entire data set. You can pass completely new data set, whatever, right? So it's going to make a prediction right off that, right? So this means that I can make a new, let's say, new script, a new notebook, and then load the model and just run this one line of code instead of this entire notebook, okay? And last thing is let's look at the checkpoints, right? Remember, we made a checkpoint as well. Where is it? So we made a checkpoint. It was model underscore checkpoint.keras, right? I can go ahead and load that model. I can say load the checkpoint model. I can call it anything. I call it loaded checkpoint, and look at the summary of that one. So it seems that the one that we used checkpoint for, which was the best one, was one of the models, the networks without dropout. So that's not what we see here. All right, that was pretty much it. I know it was long, but hopefully now you have a good understanding of how we can apply deep neural network to structured data like this. And again, why do I not use deep neural networks for unstructured data? Because it's not designed to handle that. You can if you want. I can simply apply this deep neural network to image recognition using MNIST dataset. But the performance that I get is way, way, way worse than the performance that we can get using simple convolutional neural networks. So why do that, once we have better structured? So for unstructured data sets, we are going to work with different networks like CNN, like LSTM, like RNN, like transformers, and you name it, right? So usually in practice, at least nowadays, we can do deep neural networks and apply it to structured data and compare this performance with the performance of the machine learning models and see which one is the winner. All right, hopefully you enjoyed it. Until the next one, take care.